So shortly, through the examples that we will study, we will solve a series of loci problems. Now, what sort of typical scenarios might we have? Well, we could have, for example, a point P varying on a curve. Let's suppose it's a parabola. So a point P moves along a parabola, so the curve C, and from that point one constructs another point based on some given information, other fixed points, lines and so on, and this point R moves. The point R moves as P moves, and the purpose will be to determine the equation for the locus of R as the point P moves. At the moment this all sounds very abstract. When we look at a particular example, you can look back and we'll see that this was the pattern we're following. So for example, for a point P on a parabola, we can take its parametric coordinates as AP squared 2AP, and obviously as P varies, that's the parameter, P varies, then the point P, capital P, moves. And let's suppose we can determine the coordinates of R in terms of P. So the coordinates of the point R, some point that moves that depends on little p, then we can write down an expression for x and y in terms of p. And if we eliminate between x and y the parameter p, then we get a relationship between capital X and capital Y, which is valid for all p, and that will describe the locus of the point R. So we've just outlined the method, but in particular circumstances then there may be some modification needed. So for example, it might be that the point R moves as 2 points on the parabola move. So there may be 2 points there that move. Now the coordinates of the point R might depend on the parameters P and Q. Now we won't be able to eliminate both P and Q to determine a relationship between X and Y that's valid for all P and Q, because we need more information. You can't determine specifically X and Y with no parameters. So very often we have an additional condition which relates P and Q for some reason. Well, if we then have X and Y in terms of P and Q, and we have an additional relationship that relates P and Q, then we can then eliminate both P and Q to get X and Y in terms of one another, and hence the locus. So finally in this section we're going to go back to where normals meet, and we're going to consider the problem of taking a point in the plane, say HK, and seeing what normals pass through that point. Now we already know that at any point on the parabola with parametric coordinates AT squared 2AT, the equation of the normal looks like this. Now let's suppose that we take a normal at the point AT squared 2AT and insist it passes through the point HK, then HK will satisfy the equation for the normal. In other words, H and K, the coordinates of that point, will be related to the parameter T, which is the parameter for the normal at the point on the parabola, through this expression. However, what we can see is that that expression on rearrangement represents a cubic equation for T. Now in the same way that before for tangents we could determine two tangents from a point in the plane to the parabola because the 2 points satisfied a quadratic equation, in this case we see that a parameter t satisfies a cubic equation if the normal at that point passes through hk. What that means, if we go back to this diagram, is that in general, from a point hk, one can draw 3 normals to the parabola. And because these 3 normals meet at one point, that point is called a conormal point. All the normals meet at that point. Now, it's not the case that every point in the plane can you draw 3 normals to the parabola, but it's certainly possible in some instances, and it will be where this cubic equation gives us 3 real roots. So that's the most number of normals you're going to be able to draw from a point in the plane to the parabola, and when you can do that, those 3 parametric coordinates will satisfy this cubic equation. Now let's suppose that those 3 points on the parabola have normals which pass through hk and hence satisfy this cubic equation, have parametric coordinates p, q and r, then p, q and r will be the roots of this cubic. Now if we look back at the beginning section of the notes, we'll see that the sum of the roots of this cubic will be 0. It will be the coefficient of t squared, which is 0 in this case. The pairwise product added up of the parameters can be written in terms of the coefficient of t and a, and finally the product of the 3 parameters, the product of the roots, will be given by minus the constant term over the coefficient of t cubed. In other words, from the point hk, if we can draw 3 normals to the parabola, which we certainly have here, and they meet at ap squared 2ap, aq squared 2aq and ar squared 2ar, then those 3 values p, q and r are the roots of this cubic, and they are related to the coefficients through these 3 standard expressions that we had before from the properties of the roots of a cubic. Now in particular we see that the sum of the 3 parameters has to be 0. In other words, if the 3 parameters are 0, add up to 0, then this cubic equation will have those 3 roots p, q, r, provided these 2 other properties hold. So if they meet at the same point, if those normals meet at the same point, they must satisfy this cubic, and hence the sum of the roots has to be 0. So the sum of the parameters is 0. In other words, if we take 3 points for which the sum of the parameters is not 0, then they won't give rise to a single point of intersection. Conversely, if those 3 parameters do add up to 0, then the normals at those 2 points will meet at the same point. And we can see why that's the case from the following argument. Let's suppose we take 2 normals at p and q and assume that they meet at h, k. Then there will be a third normal through that point, and the third normal through that point might have parametric coordinate, say r dashed. Well, because those 3 normals pass through the point hk, then the 3 parameters p, q and r dashed will satisfy the same cubic equation, and hence the sum of those 3 roots has to be 0. Well, if the sum of these 3 roots is 0 and p plus q plus r is 0, then r will have to be equal to r dashed, and so those 2 parameters are the same, and that third normal which passes through that point with parametric coordinates r dashed is also the same as the point r, and it was the point R we were assuming had the property that P plus Q plus R was 0. Now we can also use those same three equations that are written up the top here that relate the three parameters for three normals that each pass through HK to determine the points of intersection of those three normals, or in general just say 2, as we've seen before. So let's suppose PQR represent the 3 points on the parabola whose normals pass through H, K. So those three roots of that cubic equation satisfy this expression. Let us now eliminate between these three one of the parameters R by first of all from this first expression writing R as minus P plus Q. If we substitute for R from that into this middle equation, we have this expression, and on rearrangement we get that H can be written in terms of P and Q, and it will be this expression here. Similarly, if we take this expression here and we replace R by minus P plus Q, then we get K. So by substituting for R from the first equation into these two and rearranging, we get an explicit formula for HK. But of course H, K are the coordinates of the point of intersection of the two, and in fact the three normals. So just by rearranging the second two equations with R substituted from the first one, we can get from these two expressions the explicit formula, either this one or this one, for H and K, and of course those are exactly the same results we had before. We will now look at quite a lot of problems, in fact problems 9 to 53.